Well, hi everybody. We're going to continue our exploration of Markov chains today with a particularly fascinating aspect of them, and that is the steady state or the convergence of a Markov chain. It's so exciting and very fascinating. So, without any further ado, let's go over the screen and check out our dear friend Big Pete, our fitness enthusiast. Now, if you recall, we looked at Big Pete in a previous presentation on Markov chains, and Big Pete commutes to work or takes his car to work on different days in an effort to try and turn his commuting into fitness time. Now, I want to have a look at what happens over many transitions to Big Pete's probability of riding or taking the car. Is there a trend? Well, there definitely is, and that applies only to two-state Markov chains, which Big Pete falls into the category of because he either rides or he takes the car. There's only two possibilities. So we know that from last time that the probability of riding or taking the car on the nth transition is t to the n times the initial state matrix, yes? And we know that t is, now that looks a bit horrible, that thing in red there, don't worry. T is, okay, the now is the other two rows on the left-hand side of the matrix, that is the current situation. I've called it the I plus 1th transition, or the not R, I plus 1th transition. And across the top we've got the given, that's the previous occurrence, okay? The given is the ith transition, where the number is, the subscript is less by 1 to indicate that that's the previous encounter, okay, or occurrence. Now, have I made that clear? I hope so. Now we're going to fill in the street directory type of thingies in the matrix. That's intersections of rows and columns. There we go, there they are. And we've got R given R, right, that's top left. That makes sense, doesn't it? And bottom right we've got R dash not R given not R. That's right, that all makes sense. Now let's try and fill in the numbers for you based on the situation that we had there. We know that if he rides his bike to work, yes, 0.4, that's riding given that he rode the previous day. So that's going to be an R given R, isn't it? So let's put that there, yes, and therefore the second item in that column must be 0.6 because they have to add up to 1. And the next bit tells us that we've got if he drives his car to work on the previous day, the probability that he will ride. Okay, that's ride given not ride. Okay, so where's that on our matrix? Wait a minute. Ride versus not ride. That's top right, 0.8. Good, we've got it. Therefore, the other bottom right must be 0.2. Good, we've got our transition matrix now. That's our key to everything, guys. A key to everything. Okay, now we're going to consider what happens to the state matrix of Big Pete's situation after n transitions as n goes up. And fasten your seatbelts. This is very fascinating. We know that the initial state matrix was it was half and half, wasn't it? Yeah, it was. Okay, depending on how he feels when he gets up on Monday morning, which ain't that good sometimes. Yes, so therefore we know that the what does that say? The nth state equals, that's right, that's the general way of putting what we're trying to say here, guys. The nth state after n transitions equals t to the n times the initial state matrix. Okay, you still on board? Good. Now we're going to use the CAS handheld to explore what happens, okay? Now, when n is, that's what we're going to do. Now, when n is 1, I got my trusty handheld to just multiply t by the initial state matrix, and I got 0.6 and 0.4. Okay, so it's 0.6 probability he's going to ride and 0.4 probability he's going to take the car. Now after 5, that's t to the 5 times the initial state matrix. This is what we get. Okay, a little bit different, okay? So, and after 10 transitions, now we're starting to get somewhere. We get that. Now you see that's changed only very slightly from the previous one, okay? It's gone from 0.5722 on the R element of the matrix down to 0.5714. Now we'll do some more. We'll do 15 now, and what happens then? Oh, look, guys, it's the same. It's the same. To 4 decimal places, it's the same, okay? So that's very, very fascinating, isn't it? And that's what will happen after that. It'll basically be the same to 4 decimal places. It isn't actually the same, but to 4 decimal places it is, okay? That's all the accuracy we really want for this instance. And after 50, of course it's the same. It'll probably be, you know, you'd be probably getting down to about 8 or 9 decimal places before you'd see any difference by now. But, you know, to all intents and purposes, for the level of accuracy we want, it's absolutely the same. So it's trending. It's trending to the same steady state value. Yes! Exclamation mark. Steady state. That's what it is. It converges to an equilibrium. An equilibrium convergence point. Steady state. Aren't they interesting? And this only happens, guys, to two-state Markov chains, which is what we're dealing with anyway, so that's fortunate, isn't it? We're not going to do anything more than that. Okay, what do we got here? Now, we're saying that all two-state Markov chains eventually converge to an equilibrium, steady-state condition after a sufficient number of transitions, okay? Do you get that? Right. Now, how to find the steady-state matrix. Now, this is the bit that you need to know how to do in the exams, obviously, because they're going to ask you that. Now, it really depends, it really depends on whether you have a technology-enabled exam or a technology-free exam. That is the crucial deciding factor. Now, obviously, if you have a tech-enabled exam, well, and you know your transition matrix, what I'd be doing, guys, is I would just be going T to the 50 times initial state matrix. That's what I'd be doing, because that's basically gets you to 4 decimal places and how. And it gets you there very quickly, okay? So that's the quick and dirty way to do it, guys. That's the quick and dirty way to do it, and very effective, okay? So, for Big Pete, let's see what happens to Big Pete. I'm itching to know how likely he is to ride to work after, you know, an infinite number of transitions, e.g. 50 is good enough. Let's see. We've got that, excuse me, I've got a bit of a frog today. We've got 50, yeah, that's T to the 50 times the initial state, and what does it get us? Of course it does. We did it on the previous screen. 0.5714. Well, it's a bit more than half. I think poor old Big Pete's going to get fit, probably reasonably fit, with that kind of a probability. What do you think? Pretty good. And that's R, I called it R infinity, probability of R infinity, C infinity, or not R infinity, okay? That's really what we're doing there. So that's it, guys. That's a quick way to do it, okay? Do you get that? Now, here's a great big NB. NB for you and me, and that is the most amazing part of all this, is that, wait for it, in the initial state matrix, the proportions of R and C in the initial state matrix are absolutely irrelevant. It doesn't matter what the initial state matrix is, it only depends on what the transition matrix is as to what the long-term transition state is going to be, okay? It only depends on the transition matrix, okay? Isn't that interesting? They will all converge. All initial state matrices will converge to the same values as we just got there for Big Pete. Isn't that interesting? Fascinating, isn't it? It is fascinating. So, how do we find the steady state matrix? Again, for tech-free. Now, this is the more fascinating, more analytical way, which is absolutely beautiful and very elegant. So, stand by. It's really, really worth seeing. Okay, so we say that when steady state is reached, this is the one you would use in the tech-free exam if you had a 2-mark question and you had to show some working, okay? Later on, I'll give you the quick and dirty method in the TechFree exam if it's only a 1 mark question and you don't really have to show any working, okay? So I'll give you both for the TechFree. This is the more elegant analytical one, which appeals to me but takes a bit more time. Okay, we've got, now look at that, Tx equals x. Well, what am I talking about? Fear not, my child, it all makes sense. We're saying that when you get to steady state, okay, each time you transition your state to the next state, it makes no difference because you've already reached steady state. So therefore, transitioning capital X matrix X just gets you matrix X anyway. You see, it doesn't change it. That's what I'm saying. Therefore, yes, we're saying transitions no longer change the outcome of the proportions or probabilities that we're dealing with here, okay? So let's just, T is the transition matrix, so let's just see if we can work this out. Excuse me. So we've got X is the steady state matrix, and I'm going to call it matrix little x and 1 minus little x because they have to add up to 1 because we're dealing with proportions or probabilities in that matrix. All right. Let us proceed. The columns add to 1. Of course they do. Hence for Big Pete, here we go. T is that thing, we know that, and we can solve for the exact value of x. Instead of that 4 decimal place thing we did when we did t to the 50 on the previous screen, t to the 50 times s naught, we will get the exact value, and we're going to have great fun working out if it actually is the same value, okay? We'll do a decimal approximation of it, and I would be prepared to bet you that it'll come out the same as we got on the previous screen. So what am I saying? There's Tx equals x, guys, in terms of a mathematical way that we can now solve for little x, okay? Let's do it. So I'm saying that 0.4 times x, there, see how I'm circling them? I'm showing you what I'm doing. I'm multiplying those matrices together, at least the top line of the matrix, the first row of the first matrix, yeah, times the second matrix, yeah. Plus 0.8 times 1 minus x gets us to x, doesn't it? Now we just got to solve it for x, and I'm just doing a little bit of expanding there and simplifying a bit, and you eventually get to that line there, after you get all the x's together on one side and the numbers on the other side, and then you get to there, and then you get to there, and that's 8 over 14, of course, which is 4 over 7. So that looks like, guys, that is the steady state probability of Pete riding to work. Da-da-da-da. There it is, yes, we do see the light. It's quite amazing, and the light is bright. So therefore, 1 minus x would be 1 minus 8 over 14, which is 6 over 14, which is 3 over 7. Okay? So therefore, 4 over 7 riding, 3 over 7 carring. That's Big Pete. Now let's see. Yeah, there's S infinity. It's steady state. I've written it as over 14, but you can think about it as over 7 if you like. 8 over 14, 6 over 14, or 4 over 7, 3 over 7. Now I want to take that 8 over 14, yes, and see if it comes to the same thing as what we got on the previous screen. Yes, that's right, 8 over 14, or 4 over 7 of riding to work. Now, testing, testing, testing. Here we go. Yeah, look at that. Look at that, guys. 8 over 14 is 0.5714, which is exactly what we got on the previous screen using the t to the 50 times S0 calculation. So there, we've just done it as an exact value, and that's how to do it. Now, I want you to remember how to do that, because you need to know how to do that for the TechFree component of the exam, where you are required to show working. It's pretty neat. It's pretty neat. Okay? Yeah, we got that as before. Now, okay, this is the how to find the steady state matrix with the TechFree again. Now, this is the quick and dirty 1 mark question way of doing it. when I show you this, you're going to love this. It's really, really nice, okay? So we're going to use that same technique that we just used on the previous screen where we had Tx equals x, but we're going to generalise it now. We're generalising for any case whatsoever. And yes, we know that Tx equals x for steady state. Now, we're going to instead of using Big Pete's situation there, we're going to use A's and B's, pronumerals, okay? Because we're generalising, aren't we? Yes, we are. So that's going to be my A column. That's going to be my B column, guys, okay? Now, here we go. Watch this. See that there I've written there. Now, that's the top row of this matrix, okay? The part of the top row anyway. Now I want you, in order for you, this is just the best way to set this out in terms of where A goes and where B goes, in order for the end result to come out nice and elegant for the steady state matrix. Now, think to yourself, in terms of letter grades in an exam, A, B, C, D, E, alright? Or a test or an assessment task of some description. Now, I want you to think to yourself, this is the key. What is 1 less than an A in terms of grades? What is 1 less than an A? Well, it's a B, isn't it? Well, that's the top row of your matrix. 1 less than an A is a B. That's all I want you to remember. Just keep that natty little lyric. What is 1 less than an A? It's a B. That gets you the top row of your matrix. Now, you just fill the columns in so they add up to 1 now. So, okay, bottom left has to be what? Yeah, of course it has to be A. What about bottom right? It's 1 minus B, isn't it? Now, that's the way I want you to express your generalised transition matrix, okay? That's the way I want you to do it. Now, what we're going to do now is we're going to call capital X matrix, the same as we did before, little x and 1 minus little x. And we're going to solve it for x, okay? And they will come out in terms of A and B, okay? And you watch what happens. Yeah, they are the proportions or the probabilities which have to add up to 1. They are. The little x and 1 minus little x have to add up to 1. So we're solving for the proportions or probabilities in a steady state matrix. Okay? Good. Okay, good, we're on board. Now, I'm going to solve this now, the same way as I solved the situation on the previous screen for Big Pete using real numbers in that first matrix. Okay? Alright. Yes, 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 good, good, we're going to do that. Okay, let's go. Now, therefore, 1 minus A, that's that one, times x, which is that one, plus b, which is that one, times 1 minus x, which is there, gets us x. Okay, now we're going to solve it for x, guys, right? That's what we're doing. Good. Okay, let's go for that. Just simplifying a little bit. Great. Now, yes, the x's cancel out. How fortuitous. How fortuitous. And now let's see what we've got. Taking out the common factor, and I'm getting that. My goodness, look at this. Look at that. X is b over a plus b. Now that's nice and elegant. And that is the reason that I set up the initial matrix there halfway up the page that let t equal. That's why I set them up in that particular way, because the answers come out for x and for 1 minus x come out very, very neatly, okay? That's why you do it that way. Yes, we see the light, and it's very bright. Okay, now, we need 1 minus x now, don't we? Yeah, we do, indeed. And that comes out to be that, which comes out to be, oh, wouldn't you know it, a over a plus b. Very, very neat. Now, let's just summarise that. For t equals that thing, which is what we set it up to be in the first place in generalised form, we get the steady state matrix is, now, do you notice how I've circled that B, top right, in the line above? That's the single pronumeral entry on that line, isn't it? There was a 1 minus A and there was a B. I just want you to look at the single pronumeral item, okay, on that row. It's the B. So that's the one that goes in your steady state matrix, okay? B over A plus B, and then of course in the second row we've got A is the single pronumeral entry, so you get A over A plus B. So that's the way I want you to remember it, okay, guys? So what am I asking you to remember? I'm asking you when the initial state transition matrix, or not the initial state, just the transition matrix, 1 less than an A is a B, and then that sets up the whole matrix. And then when you're doing your steady state matrix, you look for the single pronumeral on each row of that transition matrix. That's the item on the numerator for your answer, and on the denominator it's just A plus B. And that sets you up very, very nicely to do the quick and dirty 1 mark method of getting you your steady state matrix. Okay? Yes, that deserves a box. Thank you, Mr. Box. So let's test for Big Pete if it works. Okay? So we're saying there was the transition matrix. Yes, it was for Big Pete. And there's A and there's B. Okay, so we can immediately take that without any mucking around, and we can just basically get our steady state matrix as easy as falling off a log. So we just work that out. We just work it out like that. And it comes to the same thing as we got using the analytical method Tx equals x on the previous screen, using Big Pete's actual numbers without actually having to work it all out. So you can see why that's a red hot 1 mark method of doing it in a tech-free exam. Yeah, isn't it? It's mighty good. So I hope you're getting excited. I am. Yeah, that's good. That's good. Everything's good. Now we're going to have a look at the Hertz rental car company, and we're going to do the same thing for them. Okay. We looked at them in the previous presentation as well. So we're going to work out the steady state number of cars in Melbourne versus Sydney, aren't we? Yes, we are. Right, so what is the steady state for Hertz? Now remember, guys, that this the steady state matrix just gives you the probabilities or the proportions, okay? So what am I saying there? Well, do you remember that in the Hertz, if you read that question above again, you'll notice that we weren't dealing with probabilities in our state matrices for this particular question. We were dealing with actual numbers of cars. So there were 120 cars in Melbourne and 159 in Sydney. So what you do is you use that same method that I just showed you over the page, the tech-free exam method. If it's a 1 mark question, you just simply work out the steady state matrix as being B over A plus B and A over A plus B, okay? And that gives you the proportions. But then you apply those proportions to the total number of cars, and that'll give you the actual number in Melbourne and the actual number in Sydney. Now, if you didn't get that, I'll show you, okay? It's easy as. Now we've got to get our transition matrix sorted out again. If you read the question, well, we're doing our street directory thingy here. Now, what did it say? Oh yes, all right. Look, I'm just doing it quickly for you. That was what was that? The probability of the car rented in Melbourne being returned to Sydney. So it's not Melbourne given Melbourne. Yeah, that's a 0.3. Therefore, that's a 0.7. And the other one was, what was that again? It was 0.15, that a car rented in Sydney will be returned to Melbourne. So that's not Melbourne. Oh no, wait a minute. It's Melbourne given not Melbourne. Yeah, that's the top right. So that's 0.15. Therefore, bottom right is 0.85. Now we've got it. Now we've got it. There's A. Now look how quick and dirty this is. It's just beautiful. That's A. That's B. Therefore, our steady state matrix, guys, is that. Let's work it out. Oh, wow. This is really something. Yeah, you get that. And that simplifies too. Yes, we see the light. That's 15 over 45, 30 over 45. Simplifies to 1/3, 2/3. My goodness. Was that quick or was that quick? That's it. Now, we're saying, ladies and gentlemen, we're saying that in the steady state situation, after many, many, many transitions, that you'll have 1/3 of the cars in Melbourne and 2/3 of the cars in Sydney. Now, how many cars? Well, again, you've got 120 in Melbourne and 159 in Sydney in the initial situation at the start, okay? So, how many cars is that all told? Well, let's just see. It's that. which is 279. So what I'm saying to you is this, that 1/3 of those 279 cars will eventually end up in Melbourne, and 2/3 of those 279 cars will end up in Sydney. That's how it works, because, as I say, the steady state matrix is just proportions or probabilities. In the case where you'd be dealing with, say, percentages, which also work for Markov chains, remember Markov chains work for probabilities, also percentages, and just straight numbers. Well, for the case of percentages, you would just take those proportions that we've got there and multiply them by 100. Okay? That's what you do. So, it's easy. There's the final steady state. And we've got, right, that's 1/3 of the cars for Melbourne. That's 93 end up in Melbourne, and 2/3 end up in Sydney, and that's 186 in Sydney. And Mr. Box. Isn't that fantastic? Now, how did you go with all that? It's really, really, really interesting, and it's very easy to do. So, if you are a little bit confused by what we've covered, which was quite a bit, just go back and have another look at it, and you'll see how it works. But basically, I've covered the whole idea of how to work out the steady state matrix using tech-enabled technique, where you just say t to the 50 times s subscript 0. That's the quick and dirty way for the tech-enabled exam. For the tech-free, you work it out analytically using capital T, capital X times each other equals X, capital X. Or you can just use that marvellous little A and B method that I just taught you, okay, with the 1 less than an A is a B, and so on, if you don't need to show any working. Okay, it's pretty good, isn't it? So therefore, I think we've come to the end of the road, and you are a star and you'll go far. Aha. So, thank you very much for listening, and please have a wonderful day, and I'll see you next time. Bye.